Hello! I think today is lecture 6. I hope so. So we've done a whole bunch of stuff on differentiation and integration. We found even in integration that differentiation kind of slipped in a little bit. And we saw a little bit of the stuff we did before reappear in the form of what we had to do for integration by substitution and for integration by parts. What we're going to see now is a kind of unification of the two proper in a study of a thing called a ordinary differential equation. So differential equations are a big huge field. I've got a textbook here somewhere if I can find it. So here's one such textbook you might see at uni that I kept from university myself. So part A is ordinary differential equations. So that's the first 250 pages of this textbook are just differential equations, ordinary differential equations. I'll talk about what that means in a second. And then we move on to partial differential equations later on, which I kind of skimmed through a little bit, 60 pages worth. Yeah, so there's about 300 pages of this textbook, which, to be fair, was a good how many pages are in this? You know, it's about 1,000 pages long, but it's still about a third of the book is on differential equations. It's a very important field in maths. And physics, in fact, and engineering more so, because so many different systems that exist in life are dictated and governed by these equations. So let's look at ordinary differential equations. So, in all honesty, we've actually touched upon these before. We did these in higher, or we did a simple version of these in higher. So, a differential equation is just an equation that looks at y, x, dy by dx, so the derivative of y with respect to x, and maybe d2y by dx squared, d3y by dx cubed, etc. Although, to be honest, you don't often see ones that go past d2y by dx squared. That's usually enough for us. So just equations we put together that are full of these things, and the thing about them is that they can look very simple, but can give deceptively complicated answers or deceptively wide-ranging answers. So let's just show you one. I'm not going to do it, I'm just going to make one up. So let's say we have, well, first of all, we've got yx, and we're going to be doing a lot of writing this stuff. So sometimes I'm going to write dy by dx out in full, but sometimes, to save myself some time, I'm going to say that dy by dx is equal to y dash, and d2y by dx squared is equal to y dash dash, etc. So y dash, every time you see a dash, we've differentiated it with respect to x once. And remember that instead of x I could use t as well. It just means differentiated with respect to the variable. So an ordinary differential equation is something where we've only got one variable essentially. We've only got one variable and we're differentiating by. We've got a function, we've got a variable, and we're differentiating by that one variable. We get partial differential equations, which might be where we've got a function that relies on two variables. So that'd be something that depends on x and on t, so maybe space and time. And putting together a partial differential equation with respect to that. Things like the Schrodinger's equations you've ever heard of, that's an example of a partial differential equation. And they're quite hard to solve actually. When we're doing it one at a time, they're not easy to solve, but we've got most of the methods down. It's very, very rare these days that we meet a different ordinary differential equation that we can't handle. So a differential equation might look something like this. Let's say we do 5y dash dash minus xy dash plus y equals 0. Okay, I'm not going to solve this. Looking at it, I don't particularly know how to solve it, but it's the example of something you might see. So the idea is that this is hidden, the identity of y. We expect that y is some function of x, right? It's some equation. It could be sine x, it could be x squared, it could be x squared plus sine x plus blah blah blah. Any kind of function that relies only on x. We assume that y exists in this form, and our goal is to then find what y would be, what kind of function of x would fit this template, would fit this shape. And there's a whole bunch of different methods that we could employ to do this. We're going to look at, very quickly we'll look at this kind of thing we did before. We looked at, in higher, we looked at equations like dy by dx is equal to 4x plus 3. And the way we would then find y from this, maybe have a look at it and decide for yourself how you would try and find y from this. Well, we say, well, if this is the derivative is equal to 4x plus 3, well, if I integrate this, I should get back to the function. So y is going to be equal to the integral of 4x plus 3 dx, and then we apply our usual rules. It's going to be 2x squared plus 3x plus c. And usually we're given what are sometimes called initial conditions, so we're told that, oh, by the way, we're given some coordinate. In other words, we're saying, well, when x is 5 then y is 3 or something. So we're told that x equals 5, y equals 3, and then that lets us solve for c. We go, well, that means that if y is 3, we can say that 3 is equal to 2 times 5 squared plus 3 times 5 plus c. So 3 is equal to 50 plus 15 plus c. So c is equal to 3 minus 65, which is equal to minus 62. So our actual equation is y is equal to 2x squared plus 3x minus 62. And that allows us to solve for this particular differential equation. So we found the y that fits into this shape, that gives it out, is this. When we did this just by simple integration. So you can maybe see here that this was a very simple thing here. Well, this wasn't. And the difference I think you might spot between here and here is that I've got dy by dx on one side and stuff that's just x on the other. Well, in this case, I've got y dash dash, y dash, y and x all mixed together. And that's where the difficulty comes from. How did we mix these in the first place to give such a complicated equation, and how do we work backwards from that? So that's how you'd solve the simple differential equations. This is maybe something like someone's told you the speed is equal to 4 times the time plus 3. How do you get from the speed to the displacement? Well, you integrate. We'll talk about that more in the next unit as well. Let's do the first type of these things that we can actually handle. First order separable. So let's use this opportunity to talk about what an order is. The order of a differential equation is the highest derivative that appears in it. So for example, if we had something like y equals 4x plus 3, that is 0th order because there's no derivatives in it. If we had y dash is equal to 4x plus 3, this would be first order because there's a first derivative in it. If we had y dash dash minus y dash plus 4x equals 0, that would be second order. Whoops, I didn't want to do that. Second order. And I've changed my formula as well, sorry. Second order differential equation. So it's just the highest order that appears. So if we're doing first order, this means that we're only looking at y dash equals, or dy by dx equals. Separable means that we're able to divide this thing, so we've got y's on one side and x's on the other. So let's have a think. Let me make one up and we'll see how we can solve it. First order separable, so dy by dx minus 6x is equal to minus 6x over y is equal to 1 over y. Something like that, something dumb. I'm just trying to make up something that involves a couple more steps. So our idea here is that we want to separate this, hence the separable. Because if we can separate this into two things, we'll get to that in fact, and then I'll show you, but we want to separate it so we've got things that are in terms of x and dx on one side, and in terms of y and dy on the other side. Or in fact, the other way around, from which my hand's gesturing there. So let's do some algebra on this first. So dy by dx is equal to 1 over y plus 6x over y, which you might put together to be 6x plus 1 over y. And then what we want to do is like a little cross multiplication type thing. So we can multiply that side by dx, so dy is equal to 6x plus 1 over y dx, and that means that when we multiply that up by here, we get y dy is equal to 6x plus 1 dx. And that's great, because this is saying that all the y's on one side equal all the x's on the other side. If we've managed to do that, if you've managed to isolate it, remember your algebra has to be good to do this. You're not necessarily guaranteed to be able to do this, just looking at it. If you're able to reorganise this so it looks like y's on one side, x on the other, well, we can just stick integral signs in front of it. Y dy is equal to integral 6x plus 1 dx. Because this line is saying that, okay, all the y's times the little changes in y are equal to 6x plus 1 times the little changes in x's. And this is saying if you add up all those y dy's, you get the same as you add up all the 6x plus 1 dx's. So it's perfectly okay to do this, as long as you've got a dy on one side and a dx on the other. You're not pulling the dy and dx out of nowhere. You've got them to begin with. You've broken that up, taken that dx up here. Then you can do this. So this tells us, when we integrate this side, we get y squared over 2 plus c is equal to, if I integrate that, you get 3x squared. So it would be x squared over 2, so put 6 divided by 2 is 3, plus x, plus, and now I've already got a constant over here, so I need to get another constant, call it d. So this implies, I'm going to do this quite quickly, it's going to be y squared is equal to, before I do that, c and d are these unknown numbers, so a constant of integration from that one and a constant from integration of that one. It's an unknown number plus an unknown number. It's going to be another unknown number, so let's just call it, stick them together and call it an extra thing. So c plus d is equal to, and I'll do c wavy line. It's just some other unknown number that's not quite the first two, but we didn't know the first two in the first place, so we're going to call it c wavy line. So that's, in fact that's going to move there, so let's just call that minus c plus d to anticipate what's going to happen there. So y squared is equal to 6x squared plus 2x plus c wavy line. So y is equal to the square root of 6x squared plus 2x plus c wavy line plus some unknown number. That's us solved the differential equation. This is the equation that if we were to differentiate it, take away 6x over y, we'd be left with 1 over y. That's what this tells us. I could go through and prove that. I'll leave that as an exercise to you guys to prove. Try and differentiate this and see if you can slip that into that equation and make it fit. Or in other words, if you differentiate this, you should get this. So this is what we mean by first order separable. First order because it's dy by dx, separable because we separated it. And then our method is just to divide x's on one side, y's on the other side of the equal sign, and then stick integral signs in front of each side, integrate with respect to each variable, so integrated y with respect to y, and integrated x with respect to x, and then just put it all together to make y the subject. So I have been a bit slap happy here as well, because I should have made that 2D really, should it have, or 2c dash at least, but it doesn't really matter. Again, it's an unknown number, so it is important that the unknown number is underneath the square root sign and not outside the square root sign, but it's not important whether it's c dash or 2c dash or 2c dash plus d or whatever. It's just an unknown number. We shouldn't pick hairs over adding unknown numbers to unknown numbers. Okay, so I'll do one more. There's one I like the look of. Okay, so let's do dy by dx is equal to e to the minus y 2x minus 4. So this is a differential equation, and we want to solve it in order to make y the subject, essentially. So we're going to get, so do this cross multiplication thing, so this is going to come up here, and this is going to go down there. So dy over e to the minus y is equal to 2x minus 4 dx. I'm going to tidy that up a little bit more. That's e to the minus y. 1 over e to the minus y is just e to the y. Remember, we can change this, bring this up by changing the sign on the index. So that means that e to the y is equal to, dy is equal to 2x minus 4 dx. And then I can stick integral signs straight in front of that to say we're going to add up all these little bits. So integrating e to the y, we did that previously in this unit, is just going to be e to the y, there's no constant in front of it, is equal to 2x integrated is going to be 2x squared over 2, so just x squared, minus 4x plus c. So what I've done here is I've just put the constant at the end of the whole thing. There would have been a constant in here and a constant here that I've combined to give, but it saves time just at this stage to just call it c. So this is almost good, but we want y equals, we don't want e to the y equals. So we undo an e to the y by taking logs of both sides. So that says that y is equal to ln x squared minus 4x plus c. Oh, and the question that I'm copying off my computer monitor here is, it also tells us the clue that y, when evaluated at 5, is equal to 0. So we can say that 0 is equal to ln 25 minus 4x, 4 times 5 plus c. Let's probably would be better to insert it in here, but let's raise both sides to the power of e. That says that e to the 0 is equal to 25 minus 20 plus c. E to the 0 is 1, so 1 is equal to 5 plus c, so c is equal to negative 4. So our equation is actually y is equal to ln x squared minus 4x minus 4. There we have it. So separate and solve. So that's the first type of differential equation that we can actually solve. It's worth maybe pointing out that we're learning some particular types of differential equations in order to see how to solve them. This is not an exhaustive list. Once you've done these 1, 2, 3 different types of differential equations I'm going to show you in this unit, it doesn't mean you'll definitely be able to do all of them, or even any of them that make it shown that come up naturally in nature. These are what are called linear differential equations, which just means that all the derivatives appear to the first power, not to the first derivative, but the first power. If you were to do something like dy by dx and put a squared around that, then you'd be in trouble. They suddenly become very hard to solve. So these linear differential equations we can do most of. It might be all of, but it's definitely at least most of. But as soon as they become non-linear, that's when things become a bit harder to solve. Okay, so the next one we're going to look at is a kind of constructed form. Not a constructed form, one that might pop up, but one that we can get a solution for because we can do kind of some crafty maths to it. So a long time ago we derived a method to solve the ones that come in this particular format. So we've got a first derivative here, plus y undifferentiated times some function we're going to call p of x. So it could be sine x, it could be x squared, it could be x cubed, whatever we want, equals some other function q of x. Again, this could be another function, doesn't really have to be, there's no constraints on what these functions are, except that they're only functions of x. So what we do is we look at this and we say, well, something a bit familiar is going on here. We've got f dash here, or y dash here, sorry, and just y times something here. And we go, this looks a bit like the product rule. If you think back to the product rule we did in differentiation, that said that if we had f, let's call it df by dx, times g, plus f times dg by dx, that would be the same as df times g by dx. So this looked quite close to this. We've got three terms. We've got the y term is undifferentiated here but differentiated here. We don't have a g attached to here, and we don't have a convincing reason why that would be g dash. So what we're going to do is just sort of brute force it. We're going to say, let's come up with something called mu, which is a function of x. We assume it's a function of x. Maybe it's just a number. We're going to assume it's a function of x and call that mu for now. So I'm going to multiply this equation here by mu, multiply it all the way through. So that would give us dy by dx mu plus y p of x mu equals q of x mu. So let's compare these things quite closely. This would suggest that if f is equal to y, let's start with there, or y is equal to f, whatever way you want to look at it, g would be equal to this mu thing, and if f is y here, then that would say that dg by dx is p of x mu. And then even better, compare these two things. We have that df and g dx is equal to q of x mu. So if we move that across, we get dfg equals q of x mu dx. Integrate both sides, we get f times g is equal to the integral of q of x mu. Let's leave that sort of unknown at the moment, we're only going to integrate this side, sorry. And then this tells us that if I wanted to make f the subject, that would be 1 over g times q of x mu dx. We know that f is y, we know that g is mu, so this tells us that y is equal to 1 over mu times the integral of q of x times mu dx. So that's an important result there. So the solution, if we've got an equation in this format here, then the solution to this comes in this format. The only question is, can we find a mu which fits this form, which is a reasonable form? Obviously, I said before we brute forced it, we said we're multiplying it by mu. I don't know what mu is. I don't know whether it's a big horrible function of x. I don't know whether it's a number. I don't know anything about it. Can we now make a reasonable guess as to what mu would be? We've got these two facts here to work with. We've got that g is mu and dg by dx is p of x mu. So let's take a new page and use these things together. We've got g is equal to mu and dg by dx is equal to p of x mu. So let's put these together and decode it a little bit. We've got that, we said g is mu, so d mu by dx is equal to p of x mu. We can use our separable equation ability again. So this says that this becomes 1 over mu, so 1 over mu d mu is equal to p of x dx, sorry. Integrate both sides. Boop, boop. We get ln mu is equal to, again, the integral of p of x dx, and let's assume that the constant of integration can get absorbed by this integral over here once we do it. And then to reverse this, we can say that, well, mu is equal to, so we're going to take e to the power of both sides, so it's going to be e to the power of the integral of p of x dx. So watch your mind go off. There we go. And there we have it. We've solved for what mu is. Now it's a bit of a complicated thing. This says that whatever p of x was, we integrate it and then take e to the power of it. But this, together with our previous result, means we can solve these equations. So let's write out everything we know. We know that if dy by dx plus y p of x is equal to q of x. Oh, one thing, just in case you're ever looking this up, this thing is often referred to as the integrating factor. In other words, the factor that makes it look like the product rule and therefore allows us to integrate to undo the product rule in the first place, to get back to y. So if dy by dx plus yp of x equals q of x, then y is equal to, and we said it was 1 over mu integral of q of x mu dx, for mu is equal to e to the power of the integral of p of x. that was a lot of work, a lot of derivation there to get to this fact here. Now I'm going to give you this, or I would have given you this in a formula sheet, and you would get this in a formula sheet as well, and you'd be able to put these two things together by examining the equation you're working on in order to put them together. It looks quite complicated. It's not really if you've got these together. It's just a case of taking this, breaking it down into its p of x and q of x. So p of x is the stuff attached to y, and q of x is the stuff that would go on the other side of the equal sign, and then putting it through this ringer. Just taking it, going through this process, finding the integral of p of x, taking e to the power of it, multiplying q of x by it, then integrating the result, dividing it by mu, then set that equal to y. So let's do a little example. So let's do dy by dx plus 5 over x times y equals x. So again, we know that mu is going to be e to the power of p of x integrated, and y is going to be 1 over mu integral of mu times q of x dx. So our question then is, what are p of x and q of x? Well, p of x, remember, the original format we looked at was dy by dx plus p of x y is equal to q of x. So this tells us, for us, p of x is equal to 5 over x, and q of x is equal to x. So first things first is going to be to find this integrating factor, find mu. So we're going to say that mu, well, let's actually just do the integral of p of x, because we're going to need to find the integral of p of x to do that. So integral of p of x dx is equal to the integral of, we say p of x was 5 over x, which is equal to 5 ln x plus c. So one pro tip is that, for reasons we can kind of, I'd rather not discuss at the moment, they're not too complex but they can be a bit hard to get across, is that this plus c isn't necessary here. When we take e to this power here, so let's say, so mu is equal to e to the, let's just trust me here, just trust me that we don't talk about the integrating factor at the constant integration at this point for the integrating factor. It's not a cheat, it is perfectly valid because we can do some multiplication or division together later, but we'll maybe discuss this. It's a bit much for me to get across at the moment. So we can, when finding the integrating factor, we can forget about the plus c when we do the integration for the first time. So mu is going to be e to the 5 ln x. Now we're going to have to think a bit about our rules of indices here in order to get a decent answer. So we can think about that as e to the 5 times ln x, which is the same as e to the ln x to the power 5. Remember, when we take a power to another power, it's the same multiplication, same backwards. Multiplication is the same as a power to a power. And e to the ln x, they cancel each other out. So we get just x to the 5. So mu is x to the 5. Unbelievably, after all this nonsense we went through, we got a really reasonable looking integrating factor at the end, x to the 5. So y, to put this in here, is going to be 1 over x to the 5 times the integral of x to the 5 times, and q of x was x, dx. So that's equal to 1 over x to the 5 times the integral of x to 6, sorry I've done that a bit early, dx, which is equal to 1 over x to the 5 x to the 7 over 7 plus c. Now this is infuriating a little bit because it means that this plus c is knocking us off, so we can't just divide through by x to the 5, but this is the answer. This is the answer. Okay, I'll do another one. Let's do a sort of coupled one. Let's do x dy by dx plus 2y equals 10x squared. And we're also given the clue that y of 1 equals 3. So again, we're comparing this to dy by dx plus y p of x equals q of x. And we have a big problem here. Or something that looks like a big problem here, in that we've got an x attached to this dy by dx, which usually, maybe if you are panicky like me, panic and look and see, oh, that x is there, we can't use this format. But if we do a bit of algebra on this thing first, we can reformat. In other words, we can divide through by x. So dy by dx plus 2 over x y equals 10x. See, that's much better. So I've taken this and divided through each term by x, and we get something that matches this format exactly. So we've got that p of x is equal to 2 over x and q of x is equal to 10x. So let's integrate p of x. So the integral of p of x is equal to the integral of 2 over x, which is equal to 2 ln x. And remember, I'm going to say plus c in brackets, but we forget about the plus c and we use it as an integrating factor. So mu is equal to e to the 2 ln x, which is equal to e to the ln x squared, which is equal to x squared. Now you need to remember that this is the same trick came up again. Not necessarily going to come up every time. It could be something different. It could be harder, but most of the time for the sort of questions we like to ask, we'll keep it like this because it makes this cancellation relatively simple to take care of. It makes it so that this x squared communicates well with the q of x, which is going to be 10x. You can see if we divided by that or multiply by that even, it would be fine and dandy. Okay, so don't learn this as if this is something that always happens, but at the same time get used to doing it, because it is the kind of thing we'll ask you to do, though not necessarily the differential equation will show up. Anyway, so we've got the integrating factor. We know that y is equal to 1 over mu times the integral of q of x times mu d of x. Stick that stuff in. So it's 1 over x squared times the integral of 10x times x squared dx. So that's 1 over x squared times the integral of 10x cubed dx. So that's 1 over x squared times 10x to the 4 over 4 plus c. We do remember the plus c for the final answer, and that'll be us. So it's all just identify p of x, identify q of x, use your formula sheet to work out what mu would be from that, use a wee bit of your integration knowledge and your index knowledge, and put it all together in the format that this thing tells you, and integrate again, obviously. Okay, I'm going to end this lecture here. There's one more thing in this first unit to look at, which is a much easier form of differential equations. It looks harder to begin with, but actually turns out to be easy peasy. I'll try and fire that out soon. But for now, let's call that a day. Thank you very much, and I'll be on Teams to talk about how we want to approach this. Okay, see you soon. Bye.